From MiL to HiL, HIFI elements with Halil and Paul. Halil, Paul, are you there?
My name is Halil Ibrahimadam, and I would like to give information about use case A and MiL to HiL transition. And I would like to start with general overview of the use case A. Use case A is focused on high efficiency e-motor replacement to battery electric vehicle in simulation environment. To do this, component models are developed by involved partners according to HiFi standard system architecture ELEMA, and they are tested in co-simulation environment. With help of ELEMA and MiL and HiL test case activities, a faster market introduction can be possible. Also, the total effort in terms of development and calibration can be reduced. In our use case, we have two main scenarios which are separated as model in the loop, where we perform e-motor replacement and hardware in the loop. For model in the loop, our reference vehicle Fiat Doblo are tested on dynamometer, and necessary data are taken over CAN network. After that, all developed component models are automatically integrated to co-simulation platform X mode with help of SciNet, and at the moment we are performing e-motor replacement with just a few mouse clicks, and this is the beta of HIFI-ELEMENT project. For hardware in the loop test activities, all real-time capable component models are tested with physical inverter and e-machine in hardware in the loop test bench that is illustrated by shown figure. Also, I would like to show a video to introduce our hardware in the loop test bench that is located in McGahan University Center of Mobile Propulsion building.
Welcome in the electric machine test bench inside the CMP, in which the hardware in the loop testing for the HIFI-ELEMENTS project takes place. I'm Tim Faber, and I'm going to show you the test bench right now. The main components of the test bench are the device under test, which is in this case a YASA P400R axial flux machine, and the load machine, which controls our desired speed. Both machines are connected mechanically via a measurement flange, which transmits the measured speed and the measured torque to the test bench automation system outside the test cell. Electrically, the load machine is connected via these gray thick cables to a frequency converter on the upper floor, which also incorporates the speed controller. The device under test is connected via these orange lines to the traction inverter on the AC output, and the inverter is connected on the DC input to a DC sync source on the upper floor as well, which can be adjusted dynamically from 0 to 800 volt DC. Next, I'm going to show you the conditioning system of both test objects, the inverter and the traction machine. In order to test the test objects at different temperature levels, we designed a conditioning system which operates from 15 to 100 degrees Celsius dynamically. Temperatures below the freezing point are also achievable with the additional chiller unit, which is not installed at the moment. The conditioning system can handle both oil and water conditioning with a flow rate up to 20 liters per minute. In this case, the electric machine is oil-cooled and the inverter is water-cooled. Throughout the entire test cell, we installed numerous sensors for analysis and safety purposes, such as temperature sensors, oscillation sensors, flow rate sensors on the conditioning system, or electrical sensors for current and voltages on the electrical side. The data from all these sensors is gathered here in this evaluation unit. On the upper shelf, we have the evaluation for temperatures, flow rates, pressures, and oscillations. And on the lower shelf, we have our power analyzer for all DC and AC currents and voltages. The gathered data is then sent via a CAN bus to the test bench automation system outside the test cell, which I'm going to show you next. Here we are at the operator stand of the electric machine test bench. On the right, we have the mentioned test bench automation system, which receives all data from the test bench and controls the test bench by incorporating specific controllers and transmitting demand values. Moreover, we can connect the test bench automation system to a real-time co-simulation platform via a 1 kHz EtherCAT network. For the HIFI-ELEMENTS project, we use an FEV-XMod co-simulation platform. On this platform, the driver behavior, the environment, as well as the entire vehicle, besides the traction inverter and the traction machine, are simulated, and the measured signals from the test bench are integrated into the simulation. Depending on the measured values, as well as parameters of the simulation, the demand values for the test bench are simulated and then transmitted back to the test bench automation system. This forms our hardware in the loop, a so-called closed loop setup, which enables us, on the one hand, to analyze the behavior of the real component within a realistic simulated environment, and on the other hand, to calibrate controllers interacting with the physical component early in the development process. This was a wrap-up of our electric machine test bench.
At the final, I would like to show some test results and what we achieved. As you can see, we managed to follow target velocity in both cases. We are just so small deviation, but it is acceptable level. In the second graph, you can show the requested torque by VCU. Other than that, the result looks good and it is acceptable. Thank you for your time and listening.
Thank you very much, Halil. So I presume we now move on to Paul.
Paul McGahan from Ricardo. I'm going to talk briefly about moving from model in the loop, or MiL, to hardware in the loop, or HiL, in the context of virtual battery pack development. The key objective of this piece of work was to test and prove the benefits brought by virtualizing of the battery pack, starting from early concepting phase and progressing through the development process. To achieve this objective, we focused on a reference vehicle. In our case, as you can see in the bottom right, the Iveco Daily electric vehicle variant, of course exploiting the modeling toolchain as part of HIFI-ELEMENTS, which you can see stylistically represented on the top. We encountered a number of major challenges along the way: how to rapidly and automatically calibrate one model to another or to a set of physical test results, how to seamlessly exchange battery models in a co-simulation toolchain, and how to create system co-simulation models that can be easily transferred from model in the loop to hardware in the loop. On the coming slides, we'll talk a little bit about how we've overcome those challenges to meet our project objectives. So from concepting to co-simulation, we've developed a systematic workflow that we use now to rapidly create and objectively assess battery pack concepts, with a not insignificant 78% reduction in setup effort being gleaned from this approach. It's systematic in the sense that we start with a number of cell candidates. We create cell models of differing fidelities, including BMS, electrical, aging, and thermal. And this comes back to a question that was asked of Jens Ewald earlier on this morning about the computational burden for both model in the loop and hardware in the loop. We're flexible. We can build a model that's very simple to represent a battery, or that's more complicated depending on the analysis that needs to be conducted. Scaling that cell model to battery pack with, again, a number of techniques depending on the target analysis. Injecting of the battery pack requirements, typically cascaded from system or vehicle level in this case, and then the objective assessment of the alternatives using a numerical optimization-based approach, resulting in a set of concepts to be taken forward for further detailed analysis. In this work, we focused on 3 particular cell candidates. There was the pouch cell that had been selected for the Iveco reference vehicle, a cylindrical cell variant, and a novel cell technology based on lithium sulfur, which we assessed in detail. We exploited the standardized model interface definitions to seamlessly couple these concepts into vehicle level simulation and perform model in the loop simulation, analysis, and optimization. And we did this on the XMod vehicle platform, exploiting the component models developed by other partners. And this is a second question that was raised to Jens earlier this morning on what's the secret sauce. To our mind, collaboration is key. A highly representative vehicle model is created, including key features such as vehicle dynamics, thermal system, power electronics, electric motors, and control strategy. And we developed customized tools that allowed us to really rapidly assess performance against both model variants and or test data. And as an example, you see on the bottom right, on the left correlation matrix is a comparison of the terminal voltage of our battery pack against different model variants and indeed against test data. And on the bottom right is a comparison in a similar flavor of the state of charge, again, between different model variants and indeed measured data. Moving forwards to cell-in-the-loop testing concept, targeting a reduction in testing effort due to fast preparation and automated testing, testing of concepts, including BMS, without having physically available prototypes, and enabling a high repeatability of such tests. In this case, we have an architecture setup consisting of a battery model. We don't need a vehicle model in this case because we're dealing with the module level where we're conceptually investigating module configurations. The battery model connected to a test bench controller, in turn connected to real-time embedded system, which is delivering set points to the cell cycler and thermal chamber. Again, resulting in a not insignificant reduction in model exchange effort of up to 66%. As an example of the type of analysis that we've been able to conduct, standard constant current discharge cycles, constant current, constant voltage charge cycles, duty cycles such as NEDC, WLTP, real-world mission profiles given to us by our OEM partner, Iveco in this case, and indeed failure tests to investigate performance of BMS functionality. And the figures here that you're observing on the top is a comparison of the modeled averaged terminal voltage against a number of real cells under tests with the corresponding duty cycle in terms of load current on the bottom to show that we can really begin to rapidly assess module concepts even without the availability of physical prototypes. Moving forward once again to module hardware in the loop testing concepts, again with the target to automate testing, so no driver required, faster test preparation. We can test components even in the early stages of development in a controlled environment with a high repeatability. In this case, achieving, again, a not insignificant 81% reduction in testing effort. Using the XMod platform, coupling in this case a prototype module with the rest of the battery pack virtualized with the vehicle model developed by the other partners on the consortium. Looking at the physical side of things, we've leveraged the prototype battery module built as part of earlier work on the project. Placed in a controlled environment with conditioned ambient and coolant temperature, the module itself placed within a battery cycler, additionally instrumented with detailed or accurate instrumentation such as load current, temperature sensors, and voltage sensors. On the software side, of course, it's a co-simulation supporting various simulation tools from MATLAB Simulink, also exploiting the FMI model exchange, and indeed Cooley software, where we've represented the vehicle thermal modeling, and it's deployed as an FMU to our XMod platform. Also, this platform has enabled us to, even at an early stage, test advanced BMS functionality already embedded within our system, from novel state of charge estimation techniques and novel cell temperature estimation techniques via thermal modeling. Thank you very much, and I'm happy to listen to any questions.
Thank you very much. Yeah, we still got time for a question. Have I understood it correctly? You've separated MiL and HiL. Do these things not flow into one another? Are they actually separate things?
They're very tightly integrated, but in this workflow that we showed, we'd start with a model in the loop analysis, no hardware required, but exploiting those standardized interfaces, we can very quickly transition to a hardware in the loop with the same essentially setup where we virtualized what we need to, but we test physically what we have available.
Okay, there's a question here from Alain. He says, what do you call MiL? Is that pure simulation?
In the context of this work, yes, it's model in the loop and it's pure simulation.
Okay, and the next question from Alain is simulation at the system or at the vehicle level?
In our work, we had simulation at the vehicle level, where we've injected into the vehicle model the various mission profiles that were given to us as part of the requirements from the OEM, in our case, Iveco. Okay. I have a final question here from Horst, who asks, did you compare the standardized model interfaces of the battery model to those of HIFI-ELEMENTS and OBELICS? So we've we've explicitly utilized the standardized interfaces from HIFI-ELEMENTS. We've not considered standardized interfaces yet from other projects, should they have proposed their own. We've focused on exploiting the proposed interface standards developed as part of this project.
Okay, great stuff. And Halil, thank you very much for all your work before. Paul, thank you very much.